This is Physics 2 Lab 4 Circuits by Alex Sawatzka, Spring 2023. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel using energy conservation and current conservation. It is also to use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. We use these formulas to calculate the change in voltage and other things throughout this lab. The results of this lab, we found that the series circuits had a current of 0.02 amps, and we found the potential difference from running a parallel ammeter and found the RC value of 4.137 seconds, which ended up being similar to our expected value of 6 seconds. We are assuming that this ideal circuit in the simulation would effectively represent a real circuit. The circuit we are modeling has components that do not contain their true values because they have their modeled values. This will lead to differences when investigating with a real circuit. The system in this model is the circuit, and the surroundings is everything else. Using Ohm's law and the diagram given, we were able to calculate the current at 0.02 amps before building it in the circuit construction kit online with the same outlook, and had the same calculations on the ammeters with a value of 0.02 amps for the current. Then we used the voltmeter. We got a reading of 3 volts, and when we did this, the current went to 0. Using the loop rule, we get that the sum of the change in voltage of a loop is 0, and the results of each segment, the change in voltage from B to A was 3 volts, the change in voltage from D to C was negative 9.96 volts, and the change in voltage from F to E was negative 2.04, and the rest of the segments had a change in voltage of 0, and when we add these up, they cancel out to 0 volts. Then we put an ammeter in series with the 100 ohm resistor. We found that attaching the voltmeter doesn't influence the ammeter, since the high resistance of the voltmeter allows little current to flow through, which doesn't significantly influence the total current. We also found that when we connected the ammeter in parallel, the current increased to 0.06 amps because this allowed the current to go around the resistor and prevent that resistance. Then we calculated the resistance of each resistor. For the RC circuit, we found that the light becomes bright and then dims over time when connected to the battery. We found the same effect occurs when only connected to the capacitor. Charge time was with 10 ohms, it was 14.3 seconds. 20 ohms, it was 18 seconds. Discharge time with 10 ohms was 19.3, while with 20 ohms, it was 29.8. Here's the breakdown of the time-dependent voltage and the current in the DC circuit. We see that the slope of the values was calculated to end up being negative 0.2481. This is when we took the natural log of the change in voltage divided by the change in voltage naught. Then to find the resistance of the RC circuit, we're going to take the absolute value of the inverse of this, being 4.137 seconds, which ended up approximately being equal to our initial expected value of 6 seconds. Now we get to the what if, and first we ask, if we were doing this lab in real life and use an actual ammeter, what would be different and how it would have affected the circuits. We say that a real ammeter would have had some resistance affecting the current of the circuit, and the values in the reading would have been lower due to this resistance if this model were done in real life. Then we ask, if we used a real battery to charge a capacitor, how quickly would our ideal model predict a capacitor to reach full charge, and would this happen in real life? We said the model in real life would take some time to get full charge, as opposed to our simulated model, which immediately charged. This prediction would not happen in real life due to some resistance from all the components in the circuit. Thank you.